This is test number 1 of my own custom SNES game. In 3, 2, 1.
Yep, that's me. You're probably wondering how I got here. Back in 1983, Nintendo released the original Nintendo Entertainment System, but it wasn't the tech inside this box that made it so great. Even at that time, the CPU it used wasn't cutting edge, but you'd be hard-pressed today to find a console whose games are even remotely comparable. It's literally classic after classic. And the reason these games are so good comes down to this infamous little sticker, the official Nintendo seal of quality. Well, actually, it's the grueling process of submitting your game to Nintendo for them to scrutinize, sanitize, and slap on the sticker that made it so that not just any shovelware developer can write a game and publish it for the NES. I mean, legally, there was nothing stopping someone from making their own NES game. It's just that most of the time, cartridge manufacturing was done by Nintendo itself. But you could always make your own so long as you can source your own proprietary Nintendo lockout and mapper chips. But even if you play ball with Nintendo and get your game approved, better hope you order just the right amount of cartridges to not miss out on potential sales, or wind up with 20,000 copies of nuts and milk in storage. By 1991, with the release of the Super Nintendo Entertainment System, Nintendo was offering decent third-party developer support, providing everything from proper SNES dev kits, compilers, system documentation, and a well-documented game submission process. Of course, these materials were only distributed to pre-approved game developers, so there was still no way for an independent developer to make their own game, until there was a leak. This is the SNES Development Manual. One part SNES Technical and Programming Guide, one part tutorial on how to submit your game to Nintendo. Now, this isn't new, it's been leaked for decades at this point, but it's absolutely fascinating to read about all the rules Nintendo put in place for games, from the little things like no mentioning the in SNES territory, or having to submit the binary for the game to Nintendo on an MS-DOS 3.5-inch floppy drive, along with a complete instruction manual and VHS tape of the entire game being played, no video cuts and no game cheats allowed. So what does it actually take to make an SNES game? From understanding the hardware to generating a game idea, learning how to draw, programming the entire thing in assembly, creating a set of custom tools to speed up development, making 3D pre-rendered graphics, playtesting until the game actually feels fun, then finally producing a custom SNES game cartridge, shipping it off to Nintendo, selling 1 million copies, and getting on the cover of Nintendo Power. Sounds like a 2-week project to me. First, let's crack the system open to get an understanding of the hardware. Down here is the Ricoh 5A22 CPU, referred to internally as the S CPU. It's based on the 65C816 with a few more additions, but it's more or less a 16-bit extension of the classic 6502. In fact, this CPU actually starts in 6502 emulation mode, much like another CPU family I know. But the SNES is not backwards compatible with the NES, even though the SNES has access to 128 kilobytes of work RAM, quite the difference compared to the 2 kilobytes of the NES. Still, the way the picture processing unit works in the SNES is completely different than the NES, and not just because there are actually 2 PPU chips, the SPPU1, which renders the character graphics for sprites and backgrounds, and in some cases applies transformations to them, and the SPPU2, which applies other effects like mosaics, windows, and color math. Programmatically, these 2 chips can be thought of as one PPU unit with access to 64 kilobytes of video RAM that operates independently to produce the 256 by 224 video output. Then nearly the entire left side of the board is dedicated to sound. There's the Sony SPC700 CPU, sound DSP, and 64 kilobytes of PSRAM. And while the picture processing unit and audio processing unit operate independently, it's the main CPU that transfers data over to the other 2 systems between bouts of running game code that drives the audio-visual portion of any game. Of course, like most consoles of its era, the SNES is a headless computer. It has no internal program code. To do anything, it needs a cartridge, providing anywhere from 1/4 megabyte of program code, graphics, and sound data to 4 megabytes or more. While the SCPU does have a 24-bit address bus, equaling a 16 megabyte address space, it isn't all laid out sequentially. The memory map of the SNES is usually drawn with the vertical axis representing 64 kilobytes of space, and the horizontal axis representing 256 of these 64 kilobyte banks. The computer's main 128 kilobytes of work RAM is mapped to banks 7E and 7F, with the first 8 kilobytes of bank 7E being mirrored from banks 0 to 3F. Then there are certain CPU, PPU, and other I/O registers used to transfer data and other information between memory and the PPU or APU, set the background mode, read the Joy-Cons, etc. These registers are located sporadically throughout addresses 2000 to 5FFF in bank 0, again mirrored up through bank 3F. Additionally, this entire lower section of memory is also mirrored from bank 80 through bank FF, with the rest of the memory map left for the cartridge to make use of. Regardless of cartridge type, the cartridge header is made to be accessible at bank 00 address FFCO onwards. The two main kinds of cartridges are low ROM and high ROM carts. For low ROM carts, their ROM starts at bank 80 and it can extend all the way up through bank FF, but only using the top 32 kilobytes of each bank from 8000 to FFFF. This is mirrored on the lower banks of the memory map as well. However, if the cartridge comes equipped with what they call fast ROM chips, then only the higher ROM banks from 80 to FF can be accessed at higher speeds. Static RAM, as in battery-backed RAM for save data, can be stored starting at the bottom part of bank 70, and depending on the size of the SRAM chip can be stretched or mirrored into bank 7D, though typically you'll never see more than a couple of kilobytes of SRAM at a time. The second main type of cartridge is a high ROM cart, which can fill the entire address space from bank CO onto the very end, but only the top half of the ROM data is mirrored between banks 80 and BF, and the entire top half of the memory map is mirrored on the lower half as well. SRAM on a high ROM cart is placed in bank 30 between addresses 6000 to 8000, and either continued on or mirrored through bank 3F. There are other cartridge models known as extra high ROM and extra low ROM and some other versions as well, but as for me and my game, we will use the high ROM cartridge model, which means that the game ROM is 4 megabytes in size. That's 4 megabytes for all the graphics, code, and music. Now, even though I'm designing this the way Nintendo intended, I luckily don't have to go to Nintendo to manufacture my cartridges. The SNES Dev community has a couple of open source cartridge designs out there already. I'm going to go with a design from Mousebite Labs, who already has a great tutorial on how to put everything together, and where of course you get these cartridge PCBs manufactured other than today's sponsor, PCBWay, who not only were able to get these cartridge PCBs made for me, but I also need some way to program the game onto these chips, so I was able to order all the parts I need to make an open source cartridge reader, including a 3D printed case for it. They really make it as easy as just uploading, giving my specs, and hitting order. As always, extra special thanks to them. Don't forget to check them out via the link down below. So with the understanding of the hardware, it's now time to crack open the SNES Dev manual and start making a game. Okay, NDA, copyright, table of contents, okay, here we are, objects. This is what the SNES calls sprites, the independent set of pixels that can freely move about the screen. The manual also specifically notes that if the object's picture is replaced at the same time it moves, animation effects can occur. The SNES has hardware support for 128 sprites, double that of the NES. Sprites come in 3 flavors, 2-bit, 4-bit, and 8 bits per pixel. But the most common is 4-bit per pixel, where each pixel in the 8x8 tile is defined by 4 bits corresponding to an index in one of the 8 sprite palettes made of 15 colors and 1 transparent, each defined by 5 bits of red, blue, and green data. Sprites can come in a variety of sizes from 8x8 to 64x64, but at any given time only 2 sprite sizes can be used. It should also be noted that unlike the NES, whose 8x16 rectangular sprites used sequential 8x8 tiles, the SNES sprites used the horizontally and vertically adjacent tiles in VRAM, where up to 512 8x8 tiles can be stored at every 2000 offset. Each of the 128 sprites is defined by 4 bytes in a separate section of PPU memory called Object Attribute Memory, which contains the sprite's X and Y coordinate, tile number, and an attribute byte which says whether to flip the sprite horizontally or vertically, sets the layer priority, selects the palette from 0 to 7, and says whether to grab the tile from the first or second section of 256 tiles. After the first 512 bytes of OAM, there are some additional bytes that contain the high bit X value and sprite size selection bit. That's 2 bits per sprite, 4 sprites together make a byte, so 32 extra bytes for a total of 544 bytes of OAM data. When it comes to sprites for my own game, my biggest concern is that I can't draw. Seriously, I can't even draw a bath. When it comes to game design, I knew I was on the right track when I heard our generation's greatest video game critics say this.
I have seen the future of AAA gaming, and it is mostly games where you hit people with a sword.
So I've designed a game based around sword combat and adventuring. Well, swords and a bit of martial arts, since instead of the typical RPG world with elves and dwarves, I want three-legged crows and Chinese monsters whose names don't translate well to English. So I spend a lot, and I mean a lot of time drawing, watching art tutorials, throwing it all away and redrawing until I was happy with this guy. Then spent another eternity drawing out every action the player will take in 4 directions until I wound up with this, 512 8x8 tiles, which would literally fill all the sprite tile slots in VRAM. But first of all, I can cut out the left-facing tiles by simply horizontally mirroring the right-facing tiles. Plus, at any given time, I only need to load in the tiles for one direction into VRAM. So after initializing the game by resetting work RAM, VRAM, OAM, and turning on sprite rendering, I can add 2 16x16 sprites for the player. Then to move the player around, only the sprite's X and Y values need to be changed. Conveniently, the SNES has built-in registers that will automatically read the 12 bits of Joy-Con input, so I can read the values for the D-pad and move the player around the screen accordingly. To change the direction the player is facing when the D-pad is pressed in a new direction, a flag can be set to load the new direction tiles into VRAM. This transfer can't just be done at any time, only when the PPU is free during VBlink, when the electron gun in the CRT is headed from the bottom of the screen to the top. Of course, left and right use the same tile set here because flipping the tiles is determined by the sprite's attribute byte in OAM. To animate everything, it's as simple as having a list of X and Y offsets, tile numbers, and attribute values for each animation frame, then switching between these values at the right time, like through the 8-cycle walking animation, or 3-cycle player actions of either punch, kick, or block, using the animation principles of anticipation, action, and follow-through. Or if the player is holding the bronze sword, add 4 more sprites into the mix and animate the 3 actions of swipe, thrust, and sword block. And don't forget to rewrite all the animations for the other 3 directions the player can move in. And finally, 1152 bytes of animation data later, I can say that I fully understand the reason why in the early days, Mario only raised a hand when jumping and the sword animation for Link was a single animation frame. It's just a lot of work to make the right tiles appear at the right place at the right time. But there's a couple of steps I skipped before that I need to come back to. First is how SNES tiles work data-wise. All SNES tiles are 8x8 pixels, and like I said before, can range from 2 bits per pixel, like on the NES, to 8 bits per pixel. But most often you'll see 4 bit per pixel tiles. These values probably aren't stored the way you think they are. First, take a row of pixels and convert the color index value into 4 bit planes, each representing the first to 4th bits of the index from left to right. Once these bitplanes are calculated for each row, then bitplanes 1 and 2 are stored first, then in the same way bitplanes 3 and 4 follow. Formatted this way, 4-bit per pixel data is actually just 2 2-bit per pixel tiles, and an 8-bit per pixel tile is just 4 of them. I don't know why it's formatted that way, and the manual doesn't say either, but that's all necessary information for writing a program to convert the PNG data of my sprite drawings into tile data by breaking up the image into 8x8 chunks, matching the colors with a predefined RGB color palette, reformatting the chunks into SNES 4-bit per pixel tile data, converting the color palette to little endian RGB 555 color, and saving it all into a binary file that I can include in my ROM when I compile the code into an SNES game. This is necessary because I'm not just making a minimum viable SNES game, I'm building a suite of tools to aid in the game design process. But this is probably the most basic tool that I'm going to build for this project because now it's time to build the world editor. Before that, it's necessary to understand how SNES backgrounds work. Okay, hang on, I know we've all watched a million videos on SNES backgrounds, so I'm not going to bore you with the details. In fact, you don't need to know anything more than what's in this chart here from the wiki, which shows which background modes support which type of color tiles. So for most of the game, I will use Classic Mode 1, which allows 1 layer for the world background, 1 for the HUD, and 1 for the overlay text since the 3rd layer is limited to just 4 color tiles. But regardless of how many colors the layer supports, each tile map, except for that of Mode 7, is the same size. 2 kilobytes of block data, 1 word per tile covering a 32 by 32 tile area, defining the tile selection 0 to 1023, palette selection 0 to 7, whether the tile has priority, and whether to flip it horizontally or vertically. Both the tile map and the up to 1024 background tiles are kept basically anywhere you find it convenient in VRAM. You just need to tell the PPU where each layer's tile map and tiles are located via dedicated registers. Of course, the background tiles don't use the same 8 palettes as the sprites. All palettes are kept in color generator RAM, a 512-byte buffer in the PPU. Just remember that the first color in each palette represents transparency, except for the first background palette, where it defines the universal background color. There's actually quite a bit more to working with backgrounds, but this is enough information to get started on building the world editor. Once I've created some 4BBP background tiles using the Python tile tool, I can create a new web page and then use JavaScript to import the SNES tile binary file and redraw all the graphics on the canvas. This toolbox lets me change the palette, orientation, and priority of the tiles. So all I need to do is select any area from the 48x32 world map on top, then on the left I can paint on the tiles as needed. Each map area is a 32x28 screen of 8x8 tiles, but that can actually be shrunk down. There's an SNES register called background mode, which will change the background tile size from 8x8 to 16x16, effectively quadrupling the screen size covered by a single tile map, or in the case of the world editor, cutting down the export size to merely a 16x14 area of 16x16 tiles. I've designed this program so that once I export the list of world area tile maps in binary format, I can include that file and the background tiles at the end of my ROM, then set the player's map location to equal the area I was just working on, and then I can find the right memory address of the tile map to import into background 1's tile map in VRAM. Now to edit the world, I only need to change around a few tiles, hit export, compile, and the changes are right there. When the player moves, I can check if their hitbox knocks into a tile defined as a wall, or if they hit the edge of the screen, calculate the new map area, and because background 1 can now hold up to 4 screens worth of data, load in the new map into the relevant area of background 1's tile map, and use the background layer's horizontal and vertical offset registers to scroll the screen to the new area. To give life to the world, tiles like the coastline can be animated by simply changing the tile number in the tile map. But for more complicated effects, I can use the SNES window, mosaic, and color math systems. I won't go into depth, but just to give a high-level description, the window properties allow for different regions of background layers to be hidden from the screen, with a defined left and right position that can be adjusted each horizontal scanline to create different shapes. That's how effects like level transitions in Super Mario World work. But it would be just as possible to do something like only show the left half of layer 1 and the right half of layer 2. There are just a ton of possible ways to use this effect. Another often overlooked video effect is the tile mosaic, which merges the pixels of each tile from 1x1 squares, or no mosaic effect, all the way through to a 16x16 square where it's just the top left pixel color spread over the whole tile. But I think the real crown jewel of the SNES is the color math system. But before showing off how this effect blends colors, I need to have something I want to blend with the background, like a HUD, which can show the user's held weapon and current health. As opposed to the days of the NES where there was only one background layer, so the HUD just made the game feel more cinematic. These HUD tiles can be placed on background 2, but that's where the problems actually start, because background 2 is rendered behind background 1. Well, sometimes. Let me expand the background chart to show the order in which layers are rendered. Each layer has a default position, 1L, 2L, and so on, standing for low priority. But for any tile in the tile map that has the high priority bit set to 1, it will be rendered in its layer's high priority position. So operating in mode 1, the characters on layer 2 can be brought in front of layer 1 low priority tiles by setting the HUD tiles to be high priority. Now we can see them, but they seem to be getting in the way of things. I mean, what if when I design the screen, I want to put something important in the top left corner? That's where color math comes in. Up until this point, the 2 background layers and sprites have all been enabled on the system's main screen. But the system also contains a subscreen, which can have its own layers enabled, either the same or different layers, which can be used by the color math system to add, subtract, or add and subtract then half the resulting value. And what happens when you add 2 colors and split the result? You get the color right in between them, creating this half-transparent effect. Which layers are on which screen also matters, as right now the main screen has everything but background 2 enabled, and the subscreen only has background 2 enabled. But even though these sprites are set to priority 2, so they should be behind the HUD, they appear on top due to the color math process. So instead, if the main screen has all layers enabled, and the subscreen only turns off background 2, then it will properly appear on top of the sprites. Color math can also do fixed color blending, merge effects with the window system, and much more. But at this point, there's more I want to do on the game side of things that will take me beyond Mode 1. Yes, I'm going to be using the legendary, infamous, Mode 3 to make the title screen. What's special about Mode 3 is Background 1 now uses 8 BPP tiles. That's 256 colors per pixel in each tile, so the whole palette is available now. Sure, it does mean that the 32 by 28 tile area for the screen occupies nearly all of VRAM, but check this out, that's basically a low resolution picture. Plus, I do have a little room left after the tile map to store a few sprites, and I want to do something really special for the title screen, which can mean only one thing for an SNES game: pre-rendered graphics. I found the scan of a seal online, imported it into Blender, gave it a jade texture, animated it to twirl around, and then used another Python script to resize and combine the images into a single image to process into SNES tiles. The resulting 60 kilobytes worth of tile data can be included in the ROM, but since there isn't 60 kilobytes of space in VRAM, I can only import two 64 by 64 tiles at a time. But like before, I can swap them out when needed. What's really cool is that this is a single 64 by 64 pixel sprite, which is accompanied above with the game name Zero Star. And see the effect where the star is transitioning between colors? There are two ways to pull off this effect. Either spend 10 minutes making a long list of colors to run through the CGRAM index, or spend half a day carefully and meticulously writing the algorithm to calculate each independent RGB range from one color to the next randomly selected color, taking advantage of the system's special built-in multiplication and division hardware registers, all to realize that the linear feedback shift register used for the random output is deterministic. So until additional changes are made, the exact same color sequence is shown every time the game starts anyways. But hey, that 3D seal is still pretty cool. So I'm checking the calendar, and there's just no way that I'm going to get this done by the end of the year. Well, maybe by the end of this year because it's already January. But I wasn't planning on finishing the whole game right now anyways. The map itself is of a similar scale to that of Link to the Past. But right now, I'm not even sure that I can finish the demo that I had planned. So I think I'm just going to make a mini demo. Here's my first enemy, a fish out of water kind of thing that shoots bubbles at the player. Technically, they're the second enemy I implemented because I first created bamboo stalks to get object placement working in the designer and test things like action hitbox collision. But things have actually been going pretty well programming-wise thanks to all the tools. I've made it incredibly easy to add new tiles, like for my pagoda that I spend a lot of time drawing. Plus, when the player comes underneath the roof, yeah, they actually go inside. That's because these background 1 tiles are on a higher priority, which renders them above the player sprites. So it makes a really cool effect when the player enters to grab the sword. But I've also set up a special enemy outside that counts how many enemies there are and can only be destroyed when there are none left. This will force the player to learn about Kung Fu combat before being upgraded to the sword. Honestly, I've poured in so many hours into programming this game, but I've had a lot of fun doing it. And as for the rest of the mini demo, that is left as an exercise for the reader.
Now I still have one mission left, which is manufacturing a physical SNES cartridge. Taking a look at the PCBs, they finally make sense now. There's the 4MB flash for the ROM, the CIC lockout chip, the SRAM chip, and the battery for that. But I don't actually want to solder on the flash chips yet because of this. My attempt to produce an open source cartridge reader, which I would have used for programming the flash chips, but even after 3 attempts, I never got one up and running. I'm not a complete failure though. I did get it to read a single game earlier, this copy of Pokemon Platinum for the Game Boy Color, but after I tried another game, it wasn't able to read anything, so now even this game doesn't work correctly anymore. So my backup was to use this chip programmer, which I had used earlier to program the CIC lockout chip for the cartridge, and I can use this to load the ROM onto the flash chips. But I only realized that I didn't have the proper adapter for this flash chip when I was actually ready to go and solder this thing onto the cartridge. And at this point, I don't really have time to order one. So backup, this is the Super EverDrive. And while this isn't quite the hardware that I had imagined, I don't feel super bad since the flash chip on this system can only hold a single game at a time. So all I need to do is put my game ROM on this SD card, boot up the Super EverDrive, find and then load my game onto the main flash chip, and it should be ready to go. Here I am using the ultimate setup of Japanese controller plus American SNES. Let's see if my system crashes in 3, 2, 1.
I think there's hardly a better feeling than playing the game you've poured your time and talents into and seeing it all come together. Don't get me wrong here, I hit some really low points programming this thing. I swear the 8-bit, 16-bit register mode swapping will be the end of me. But while I've seen some people criticize the SNES for not having any built-in support for 3D graphics, in reality, that's what makes the SNES so great. It was the last great 2D console, the end of the great 2D dynasty. It's amazing how much was done with the technology built inside this machine. But at the end of the day, it's not the tech that makes the console great, it's the games we play along the way.
Konnichiwa.